Hello and welcome to another module of Advanced R. In this module, we will start the discussion of simulation in R. Since this is the first module, so in this module we will start discussing several functions which are associated with several probability distributions in R. That is the function which starts with D, that is like dnorm, dbinorm, dpoise, such functions like that. Again, we will discuss about functions like R norm, P norm, Q norm and so on. We will also discuss about functions like, we will also discuss about set.sit, what is it and how it is used and something like that. So, let us see what is there in this module. So, in this module, we are going to learn the introduction to basic functions associated with simulation, the use of the functions with prefix D, P, Q and R, and the use of set.sit function. So, let us start with some of the well-known basic functions. Here we will discuss about the functions that are primarily used to generate random numbers and works with probability densities. In statistics, the most popular distribution that we often come across is the normal distribution. Primarily, this is the distribution which is used most often. So, let us start with this. Whenever we need to simulate data from normal distribution, what do? How will we use R in this case? We do it using the R norm function, and this will generate data points from a normal distribution with mean and variances that you can specify in advance. Now, if you want to know the normal probability density at a point or a vector of points, then you should go for the D norm function. So, we can get the normal probability density at a point by this. What if we want to have the CDF or cumulative density function for a normal distribution? P norm function is there for our help in this regard. So, there are some of the functions which helps us to generate random numbers from normally distributed random variables, and here also to get the quantile function Q norm function will help you. So, these are some of the ideas associated with the normal distribution. But before taking up any other particular case, let us think of this from a general point of view. Whenever you want to find a probability distribution in general in R, then you may find 4 of the functions. Like in case of the normal distribution, we have seen this previously. So, let us find what are these 4 functions in general. Primarily, we may find 4 functions that are starting with D, R, functions that starts with P and functions that are starting with Q. Let us illustrate it in step by step. Function that starts with D helps us to find the probability density of a particular distribution. Function that starts with R helps us to draw random numbers from a particular distribution. Again, the function that starts with P helps us to find the cumulative distributions, and as we can think of intuitively, the function that starts with Q helps us to find the quantile of a particular distribution. So, if you compare this with the thing that had been discussed previously, there also the R norm function was used to generate random numbers from normal distribution. Again, D norm function, as we have seen it as a function with prefix D, is used to get the normal probability density with a given mean and standard deviation, of course, that had been specified previously. Again, the P norm function was used to get the cumulative distribution function for a normal distribution. So, every distribution has these 4 functions that are associated with the probability distribution. In practice, you may find a number of distributions to deal with, and in almost all the cases corresponding to each of the distribution, you might find these 4 functions. Like suppose you need to deal with the Poisson distribution. This is a very common distribution and you can expect these 4 functions corresponding to this distribution. So, what are the functions corresponding to this? Here the dPoise function gives the Poisson probability at a given point. Rpoise function helps us to draw random numbers from Poisson distribution. Ppoise function, as we know, this will help us to find the cumulative distribution function for a Poisson distribution, and Qpoise function is the quantile function corresponding to the Poisson distribution. Similar thing will hold for binomial distribution as well, as we can understand. In that case, the functions that will be used are like D binom, R binom, P binom and Q binom for the probability at a particular point, generating random numbers from binomial distribution, cumulative distribution function for a binomial distribution and the quantile function of binomial distribution respectively. So, we all know that. So, things are getting much more clear now. Just change the abbreviated name of the distributions after D, R, P and Q, and you will come up with the distributions for each of them. So, till now our discussion was based on the things which tells us which functions to use and where. But now we are more interested in how to use these functions. By this, what I mean is our concentration will now be the syntax of these functions for each of the 4 types. So, let us see how it goes. Let us start with the most popular distribution and the one we had started with, which is normal distribution. We are starting with normal distribution here. So, let us try to find what is the syntax for normal distribution. Here we will also take up some other commonly used distributions as well, and we will try to find how much the syntax of the function varies by changing the distributions. If the argument of the functions are similar, then as we know it would be easier for us to memorize all of them at one go. So, let us start with the normal distribution and let us see what these functions offers us. As we have seen earlier, we have 4 functions that include D norm, P norm, Q norm and R norm corresponding to the normal distribution. So, we are having these 4 functions that have been given here. Now, look at the arguments of the functions minutely. Let us take up the D norm function first. Here we need to give x at first. Now, what is this x? This x is the point at which we are wanting to find the probability density. Then the next thing which comes is the specification of the mean and the standard deviation respectively. Here the mean is fixed at 0 and the standard deviation is at 1. We know that this is the case of the standard normal distribution. We can specify any of the numbers which we wish to specify here as mean and standard deviation, but we are specifying 0 and 1 for simplicity. Then the log is equal to false will be included as argument here. In the cases where you want to use log of the density, then you should go for log is equal to true, but by default it takes false. Now, let us take up some special cases here, like if we fix our x at 0 for a standard normal distribution, then we need to write down D norm, then within first bracket 0, comma mean is equal to 0 and standard deviation is equal to 1. That is for the standard normal distribution, and then log is equal to false, and then we will come up to with this density. It is given here. Similarly, if one wish to take the density at some point, say at x is equal to 3, then as we all know the probability should be much lower, as we can understand it from the Chebyshev's inequality, that the probability of a point to lie between -3 to 3 is 0.9973 approximately. Now, if you put x is equal to 8 here, then what will happen? As we know that the tail probabilities are very low, so we can expect that from here also, and here as well the probability is close to 0, as we can see here. If you continue to go far more than 8, say if you put x is equal to 10, then as expected you would come up with even lesser value, and that is more close to 0. Another interesting fact is, as we all know that the normal distribution is symmetric about its mean and standard deviation, here since we are taking standard normal distribution, so this is symmetric about 0. So, if you put x is equal to 1, then you will get the probability that is given here. Again, by putting x is equal to -1, you will come up with exactly the same probability that you have got previously. So, these shows the symmetricity as well. So, the same things are reflected here as well. So, these are some of the experimentations that you can always do with the help of R and explore these kinds of functions by changing the arguments. Now, let us move on to other functions associated with the normal probability distribution. As we had seen earlier, the p-norm function provides us distribution function, and q-norm function is for the quantile function. Since the arguments in both the cases are more or less similar, so we are taking up these two simultaneously. For both the functions, log.p option is also there, and the default is false, as we can see from here. Instead of this, there is another argument which one needs to take care of, that is the lower.tail argument, which specifies the values at left. By default, it is true. If you wish to have the values at right, then the lower.tail should be equal to false. The first argument of the p-norm function takes the point at which we are trying to have the cumulative probability. So, by default, it is basically the distribution function at the point that we provide. The point is provided by us. So, let us take up some particular cases. If we write down p-norm, then within first bracket 3, comma mean equals 0 and standard deviation 1, lower.tail equals 0, and then specify log.p equals false, then we will come up with these high probability. We know that it is pretty obvious. Why? Because the tail probability is negligible in case of normal probability distribution. Now, if we substitute 3 by 2 here, then what will happen? What kind of a value that we are expecting to have here? Just apply your intuition. We all know that the distribution function is a monotonically non-decreasing function. This is a significant property of it. Now, since the argument of the function 2 is lesser than 3, so we can expect the cumulative probability to be lesser than the previous one. And exactly this thing has happened here. Have a look at the output. So, now things are getting more and more clear to us. Now, look at this. If you put 0 instead of 3 or 2, then what will happen? Since we know that the standard normal is symmetric about its mean, which is 0, so the cumulative probability less than 0 is exactly equal to the cumulative probability greater than this, and that equals 0. Exactly this is what we are getting here. So, here as well we can always do experimentation with all these kinds of functions. So, here the cumulative probability which is less than 0 is 0.5, and the cumulative probability greater than 0 is also 0.5 for standard normal distribution, as we can see from the R codes. One more thing which I want to mention here is that since the rest of the values are coming as default argument, so if you write down p norm, then only the argument at which you want to have the cumulative frequency, then also you are going to have the same result. Like here we are just writing down p norm of 0, and now look at the thing which we are having. We are having exactly 0.5 as output as it is expected. So similarly, we are considering the q norm function as well. As we all know that this function is expected to give us the point at which the probability is something that we will give. So as we can observe, the arguments will be the same as that of the p norm function instead of the first one. The syntax here is q norm, then within first bracket p, then the mean and the standard deviation. Next, the lower dot tail is equal to true, which is the default one here, and then log dot p is equal to false, which is again the default one. So as we can understand, this will give us the default of the distribution function of standard normal distribution. Now let's take up some of the special cases. As we can understand, this function is the inverse of the p norm function. So just do one thing to have a better understanding. Write down the answers that we have got previously as the argument that we need to give here. The reason is that in the previous case, we need to give the points at which we are searching for the cumulative probabilities. But here we are giving the probabilities and trying to find the points. So let's put the probability, that is 0.9986501, as an argument of the q norm function, and let's see what is happening here. We are having 3 here, as it is very much expected. Again, by putting 0.9772499, we are getting approximately 2 as an output. Remember, this was the input in the previous case by using the p norm function. So just compare the two and have a better understanding for this function. Again, have a look at the next one. Here we are putting 0.5 as an argument, or as the point where we are trying to find the quantile, and we are getting 0 as output. It implies that the probability of a point to be less than 0 is 0.5 for a standard normal distribution. We had discussed about this previously as well. Here also, since the other values will be taken as default, so if we write down just q norm of 0.5, then also we are going to have the same result as 0. So things are much more simpler in case of the r norm function. As it had been told previously that this function is meant for generating random samples from normal distribution. The syntax of this function is r norm, then within first bracket n, which is the number of samples that you wish to generate, then you need to specify the mean and the standard deviation. The default is set for standard normal distribution, so just keep on changing the different values and you will come up with a set of random numbers of your desired size. Let us take some particular cases here. If you want to have 5 random numbers from a standard normal distribution, then you will come up with these many random numbers as it had been shown here. Also, if you want to draw 5 random numbers, but with mean specified as 5 and standard deviation specified as 0.1, then we will have the random numbers which are given here. As it can be expected, here we can see that the random numbers are clustered around the mean, the specified mean 5. So this is what the r norm function is giving to us. Now, before taking up some more details regarding this, let's consider some other distributions with these functions. Let's take up the functions corresponding to binomial distribution. So we are going to have d binom, p binom, q binom and r binom functions here. So let's discuss about these functions a bit explicitly. At first we are considering the D binomial function. The arguments that have been specified are x at first, then the size, then the probability, and finally whether the log density will be considered or not. Remember, this argument is false by default. We had seen this earlier as well, so nothing to worry. Here x denotes the point at which we are trying to find the probability mass, then size denotes the number of trials. The probability argument specifies the probability of getting a success in each trial. So, we need to specify that, the probability of getting a success in each trial. So, all these are needed to be specified a priori. In particular, if you want to have the probability of getting 3 heads out of 10 trials, that the probability of getting a success is 0.5, then we should take these many things as our output. That has been given here. So, look at the output that we are getting. For the p binomial function, if you want to know the distribution function at the point 3, because p binomial function is used to get the distribution function. So, we are trying to get it at the point 3. So, you need to write this thing which is given here and do have a look at the output that we are having here. We are primarily having the cumulative probability at this point. So, if you put q is equal to 10 or q is equal to 9, then you will come up with 1 or 0.9990234 respectively, as it is very much expected. Again, as we can understand, the q binomial function will give us quantiles. So, as it had been done previously, if we insert the previous output here also and use it as input, then our output will be what we used as input previously, and here what we are getting is shown in this slide. In case of random number generations as well, things are almost same as it had been in case of the normal random numbers. Here we need to put the number of observation n, then the number of trial size, and finally the probability of successes on each such trial. So, if you write down R binomial, then total samples generated equals 10, then total number of trials equals 0, and then probability of getting ahead equals 0.5, then we will have the following output. So, we can have similar kinds of a set of 4 functions, each corresponding to distributions like Poisson, gamma, uniform, and many more. Just try to find what are the arguments that are required in each of the cases. Although this does not change that much with the change of the distributions, only the parameters do change. Like in case of normal, you need to specify the mean and standard deviation, but for the binomial distribution, the number of trials and the success probabilities in each of the trials are needed. So, the parameters are the thing which are differing with the change of the distribution. Again, for a Poisson distribution, the mean, that is lambda, is required. One more thing is always to have a clear idea of what is the form of the distribution or probability density function they are using, and try to find a relationship with the form that you are using, as you can write down a particular density function considering a number of forms. So, always make sure about this. So, we can have similar kinds of a set of 4 functions, each corresponding to distributions like Poisson, gamma, uniform, and many more. Just try to find what are the arguments that are required in each of the cases. Although this does not change that much with the change of the distributions, only the parameters do change. Like in case of normal, you need to specify the mean and standard deviation, but for the binomial distribution, the number of trials and the success probabilities in each of the trials are needed. So, the parameters are the thing which are differing with the change of the distribution. Again, for a Poisson distribution, the mean, that is lambda, is required. One more thing is always to have a clear idea of what is the form of the distribution or probability density function they are using, and try to find a relationship with the form that you are using, as you can write down a particular density function considering a number of forms. So, always make sure about this. But will you find each of the distributions in the base package? Is it possible? Of course not. So, you need to load more specialized package to use them. Like we need to load the actual package in order to get distributions like log logistic. We can find a number of such packages to deal with separate distributions. One last thing that I want here to mention is that we know how to generate random numbers from any probability distribution. In that case, we usually take the function with prefix r. Now, it might sound skeptical, but actually whenever we draw a set of random numbers from any probability distribution, then they are not actually random. We can have some pseudo random numbers instead of this. So, we can always reproduce these numbers since they are not actually random numbers. So, we can always reproduce them. But what do we need to do here is that we need to set the seed to get the numbers, same set of numbers again and again. Like suppose we are generating 10 random numbers from a normal distribution where the seed is set to be 5, then we need to specify, we need to write down these R code, and here is the output that we are having. Next, changing the seed value to 8, we will come up with a different sets of random numbers, unlike the what we had seen in the case of set.seed is equal to 8. Even if we do not mention the seed value, if we only write down R norm 10, then we will again have a different set of values altogether. But if you again set the seeds to be 5, then again we are going to have the same set of numbers that we have started with, and this is advantageous for us. So, by this way we can reproduce same sets of numbers which are always recommended from a broader point of view. So, as you have seen, in this module we had discussed about functions like dnorm, dpoise, dbinorm, rnorm, qnorm, pnorm, functions like that. We had also discussed about the syntax of these functions and how these functions are used. So, you have now the ideas of all these kinds of basic functions. From the next module onwards, we will discuss about the applications of these functions in simulation studies. So, let us stop here and let us see what is there in the next module.